Welcome once again to ECFedu blog. In this particular video, this is the continuation of momentum, linear momentum. Now, before we venture into this, I would like us to talk about, you can't talk about linear momentum without talking about isolated system, because everything happening with this law of conservation of linear momentum deals with isolation system or isolated system. Now, what is an isolated system? Isolated system. Now, an isolated system deals with an ideal assumption. Actually, it is a system where no force, where no external force is being acted upon. So if an external force does not occur or act in a particular system, we call that system an isolated system. So we are going to make an ideal assumption. Now, before that, what is the law of conservation of linear momentum? Remember, linear momentum, which is denoted by rho or small p, is mass times velocity. Mass times velocity. From our previous video, we are told that when a mass of a body is being multiplied by the velocity, what you have is linear momentum. Please be very careful. We have two types of momentum. We have an angular momentum and a linear momentum. So linear momentum deals with linear motion, a motion in a straight line. So it's not being acted upon by an acceleration due to what? Gravity. So because of that, the mass is not affected. The mass of a body is not affected. The only thing that could be affected is the velocity, which changes what? Direction. So remember, the direction the velocity takes is exactly the direction that the momentum takes. So velocity is a vector quantity. Momentum is also a vector quantity. Note that. So if you are told that a body is moving with a velocity of 20 meters per second to the north, and you are given the mass of the body, after solving, if you are asked what is the direction of the momentum, the direction of the momentum is also to the north. So note that. Now, if that is true, change in momentum, mass, which will never affect mass. Mass of a body remains constant, provided that body or substance is moving in a linear motion, not vertical motion, linear. So the mass is the same. So what changes is the velocity. So we have change in velocity, which is also called, you can say, final velocity minus initial velocity. Now, from the previous video, we are told that this change can only occur when there is the presence of what? A force. A force acting. So this change is happening at a little time, just short interval. So this short interval, let's say that we have, this will cause a force. So the force is equal to the change we have over the little time this happened. This is what the second law of Newton is stating, the rate of change. So when you cross multiply, you have that Ft, force times the short interval, is equal to the mass times change in velocity. Be very careful. But we know from here, when there is a change in velocity, automatically there is a change in acceleration. That gives us acceleration. So here is the same thing as saying mass change in velocity is equal to what? Acceleration. So this is how we got that force is equal to mass times what? Acceleration. Here, this is called an impulse. This is called an impulse. While this is called change in momentum. So as you can see, impulse, which is Ft, force times time is equal to the change in momentum. Therefore, impulse has the same unit as what? Momentum. So with this being said, now let's quickly enter into what we have now. Now we know what is momentum. Momentum is mass times velocity. So what is the law of conservation of linear momentum? So let's quickly enter into that. Now we have the law on the board. Now what does this law state? It states that in an isolated system, this is an ideal assumption, in an isolated system where there is no external force, the total momentum before collision is equal to the total momentum after collision. It's very easy law to state in an isolated system, not just any system. And I've told you what an isolated system, it means a system where there is no external force acting. That the total momentum before collision is equal to the momentum after collision. So in general, what this thing simply means is that the algebraic sum of the momenta, that is plural of momentum, is 0. Sometimes they normally ask you this question in your screening. What is the algebraic sum of the linear momentum? So by law of conservation of linear momentum, the algebraic sum is 0. Now you are going to understand, this will help us to solve different cases concerning the law of conservation of linear momentum. Now, but before we enter into that, something has come up here, which is collision. Collision. Because everything we are going to be dealing under this is all about collision. So before we enter the different cases we are likely to see that can exist under this particular law, let's quickly touch collision, types of collision we have. Now, these are the types of collision we have. We have two types of collision: elastic collision and inelastic collision. I'm going to take my time here to explain these two collisions very well. They are very, very simple. Now, for elastic collision is a collision whereby, okay, let me use this as an example now. If you have two bodies, now if two bodies collide, when two bodies collide and join together, be very careful, if they join together, now we call that inelastic, not elastic. But once the body, they collide and separate, that kind of collision is what you call elastic collision. For instance, the gas molecules. The gas molecules have perfect elastic what? Collision. What happens? They join and separate. So the molecules or atoms of a gas exhibit elastic collision. But inelastic collision is that particular collision whereby two bodies, once they join, they combine and move in the same direction. That's the simple meaning of elastic and inelastic collision. Another important thing you need to know is, in elastic collision, I want to relate this to what we have now. In elastic collision, linear, the law of conservation of energy. Now, energy here is conserved. Be very, very careful. In elastic collision, energy is conserved. While in elastic collision, energy is not conserved. So what does that mean? In elastic collision, energy before collision is equal to energy after collision, because energy is conserved. But in inelastic collision, energy before collision is always greater than the energy after collision. Now, we need to know the concept of this, because this will help us here and also in solving questions. Once we enter the different cases, we watch what is happening, the type of collision the substances or the bodies have. Then we conserve the energy, as after applying the law of conservation of linear momentum, we conserve the energy. The energy in question here is what? Kinetic energy, energy in motion. So we are going to see that in elastic collision, always know that the kinetic energy after collision, before collision is equal to the kinetic energy after collision. Why here? Energy is not conserved, therefore the kinetic energy before collision is always greater than what? The kinetic energy after collision. So let's quickly do that and see. Okay, now, like I said, law of conservation of linear momentum, in real life, this can happen in different cases. So we have the first case on the board here. I called it case 1. What this diagram here simply means is that if you have two bodies moving in the same direction, but we are assuming that the initial velocity of body A is greater than the initial velocity of body B, because that is the only case where this can occur. So if this velocity is bigger than this, there is a tendency of this particular body meeting this, certainly. Let's assume you are in a vehicle moving and another vehicle is moving faster than yours. So there is a tendency this vehicle can hit you. Yes, because it has more speed than the vehicle you are in. So that is the case we are looking at here. So this has higher speed than this. Now, when these two bodies collide, remember, this body has mass A. Sorry, mass M. MA here means mass of body A. MB here means mass of body B. UA here means U denotes initial velocity of body A. This is the initial velocity of body B. Now, when this hits this is not stationary, this is also moving, but this velocity is greater. Now watch what happens here. This is before collision. This is after collision. So this is before collision, while this is after collision. Now look at what happens here. What type of collision happened here from my explanation? You can simply see that this is inelastic collision. I hope you can see that. So this is inelastic collision. Both of them combined. As you can see, both of them combined after collision. So remember what we say, when you have inelastic collision, like what we have here, the kinetic energy differs. But before we enter the kinetic energy, let's focus about the law of conservation of this first. Now, the total momentum before collision, we have the momentum of this, the momentum of body A, plus the momentum of body B will give us the total momentum after collision. So what is the momentum of body A? Momentum is the mass times velocity. So we have MA times UA plus. Now why are we putting plus? Because momentum is a vector quantity. And we are told that when vectors move in the same direction, to get the result and the total, you have to add. So this is, both of them are moving in the same direction. That is why we have positive here. Be very careful. So plus, the momentum of the second body is mb times its velocity. Now this is equal to the combined. This mass is combined. So when both of them combine, they will move in the same direction with a common velocity v. So what we have here is the combination MA plus MB, that is the total mass, times the final velocity. As easy as that. MA plus MB times the final velocity. Addition of this will give us the total mass. So times this, that will give us the momentum after. So this is what this is called momentum before collision. The total momentum before collision. Why? This is the total momentum after collision. So if this goes here, the resultant momentum, which is called the algebraic sum, becomes 0. If you bring this over to this side, it gives you 0. So this is the first case. You have two bodies moving in the same direction. The first body has a velocity bigger than the other one. This is what will happen. And after collision, if they move in the same direction, they join, which is inelastic collision. They will have common velocity v. Once they join, they must have common velocity v. So we just simply say that kinetic energy before collision, I'll use BC to denote before collision, is always greater than kinetic energy after collision. After collision, because it is inelastic, it is not conserved, so they are not equal. It's not possible to say that the kinetic energy here is equal to this. Is not true. So this is always greater than this. So know that. Okay, now let's go over to case 2. Okay, now this is the second case. You can call it case 2. Now this is the second case whereby before the collision here, before collision, remember this is greater than this. Before collision. Now this is after collision. This is after collision. Now what happens after collision? Now after collision, if this happens, if both of them collide and still separate, that means that for this to hit this and both of them collide and separate, it means this particular body has increased the velocity of this. So the final velocity of this, in this case, VA will be less than VB. Definitely. Yes. Initially, before collision, this is greater than this. But once they collide and separate, it will add to the speed of this. So we have this. Now, with this being said, now what do you think will be the total momentum before collision? It's still the same. Now, the total momentum before collision, and this will give us ma times the initial velocity plus mb times the initial velocity, and this is equal to the law, since the law says that the momentum is conserved. So since the momentum is conserved, it is equal to this, which is ma, the final velocity VA, plus, it is positive because both move in the same direction. Always read your question very well. Always read your question to understand. So if both move in the same direction, you are adding. You are not subtracting. It is plus, not minus. So plus this, which is mb, final velocity b. Always remember, the mass does not change. Highest it can, you can add your mass, but it does not change. The mass of a body, provided it is linear motion, remains constant. So momentum is always what? Constant. Okay, so this is the momentum before collision, while this is the momentum after collision. So in this case, what we have here is elastic collision. Since both of them, they hit and separate. So the kinetic energy before collision is equal to the kinetic energy after collision. So in that case now, what is kinetic energy? Remember, kinetic energy is equal to half mass times what? Velocity squared. That is your kinetic energy. Half mass times this. So if we bring it here, the kinetic energy before collision, for this, the kinetic energy of this particular body, which is this, becomes half ma ua squared plus this is half mb ub squared. And that will give us, because energy is also conserved there, so both of them are equal. This is equal to the kinetic energy after collision, which is half mAVA squared plus half mBVB squared. So always read your question very well. So if you are asked to calculate what is the kinetic energy before collision, this is what you do, depending on the nature of the question. Now, if you are given asked to calculate the kinetic energy after collision, this is what you do. Where V, like I said, we use it to denote the final velocity here, because anything that happened here is final, while this is the initial movement. Okay, so this is the case 2, the scenario we can have. As you can see, a formula was developed for this because it is elastic collision. But in case 1, no formula was asked. Now let's check another case, case 3. Okay, now this is another case that can happen in real life. This is very possible. Now what we have here is this colliding with this. So they are moving. Still remember, this is greater than this. For that to occur, this velocity will be greater than this. Now, when they collide, it is possible for two objects to collide. You can watch two cars. When they collide and fall different direction, apart, different direction. So that means that elastic collision is still occurring here. Elastic collision. But now what changes is the direction. The direction after the effect of the collision. So now what do you do here? The momentum, the total momentum before collision, this is moving in the same direction before the collision. So we have MA UA plus MB UB. This is the collision, the total momentum before collision. Now, after the collision, let's be observant. What happened? They moved in different direction. So because it is different direction, this momentum is MA VA minus, are you seeing what is going on now? Different direction. So minus M B V B. So when you have, after colliding, they separate and go separate ways, different directions, this is what you have. So different direction gives you negative. Be very careful. Now because they separated is elastic collision, so what do you think will be our kinetic energy before and after collision? So the kinetic energy is simply half, just put half, MA UA squared plus half MB UB squared will give us half MA VA squared minus half MB VB squared. Now, you can equally expand it just like in the other, we can equally do this. What is common here is half, so you can simply say half into MA UA squared plus MB UB squared is equal to half into, because half is common here, half MA VA squared minus MB VB squared. Both of them are the same, and whether you are using this or this, you still arrive at the same formula. So this is the case 3 we have. These two colliding, separating. So let's quickly go over to case 4 and see what else can happen. Now we have another case here on the board. So we have case 4. This diagram can also occur. Now what we have here is, let's say, two vehicles coming in opposite directions. Now when they hit each other or when they collide and join together, you can see it's very possible they can collide and join together once after collision, there is a joined movement. They must have what? Common velocity, V, common final velocity. So what we have here, opposite direction, we have a minus already existing. This will give us MA UA minus MB UB, and that is equal to the addition of the masses this time around, MA plus MB times the common what? Final velocity. So this is as easy as that. Very simple, times the common velocity. So our kinetic energy cannot exist here. Why? Because energy is not conserved. This is what? Inelastic collision, provided they combine. So just know that this will always be greater than this. Energy here will always be greater than this. So I think this is easy. Let's treat another case, case 5. Okay, so we have another different case here. So this is what common sense can help us to do. So in this case now, we have case 5, the 5th case here. Both can move in different directions, hit each other and separate. That is possible. Two things can be coming this way, different direction, hit and fall apart this way. So in that case now, the momentum, the total momentum before collision is MA UA minus, since it is different direction, minus MB UB. And that will give us, it will be equal to the total momentum after the collision, which is MA VA minus MB VB. So the negative sign in anything you solve under momentum or in force is telling you that that force exited in what? Opposite direction. So after solving anything for force and you are getting negative, doesn't mean you are wrong. It's simply telling you that the thing is acting, the outcome is acting in the opposite direction. So this is what we have. So let's treat another, okay, before we treat another case, the kinetic energy. And the kinetic energy here will give us half MA UA squared minus MB UB squared. That is equal to half into MA VA squared minus MB VB squared. In solving, if you are very, very smart in solving, you can see that half can cancel half. So you can just solve with what is inside the bracket straight. Sorry. So you can solve with what is inside the bracket straight because half can cancel half. But here we are not solving yet. We are still going to meet how to solve, how to make use of these formulas depending on the question in the exercises section and in our past questions. So let's quickly do the last case here, which is the 6th case. Now in case 6 here, this is a totally different case from other cases we have been doing. What we have here is, we have two bodies, A and B, also as usual. But in this case, this arrow is telling us that this body is stationary. Stationary, it is fixed at one point. It doesn't move. Now, why this is moving? So once this moves and hits, we can get two cases here. This can hit this stationary body and join. This is the case of a bullet and a wood. For instance, if you fire a bullet, so let's say that the mass of the bullet is this, and the velocity which the bullet is moving with is this. If it hits a wood that is standing, that wood is not moving. This bullet will penetrate inside this wood and shift the wood. So the bullet is inside the wood. So both of them now are moving with a common what? Velocity. So this is the concept of the bullet and wood question JAMB normally asks. So notice that. So in this case now, what we have here is MAUA, whether it's plus or minus, doesn't matter, plus MBUB is equal to MA plus MB times this. Now this is what we have. Now, but what happens? Remember, any body at rest, stationary, has velocity of 0. So in this case, UB is 0. If UB is 0, 0 times MB nullifies everything here. So what we have here now is MA UA plus 0 is equal to MA plus MB times this. So everything now boils down, this plus 0 gives us the same thing. So what we have now is MA UA is equal to MA plus MB times V. Now this is what we have. Now this, some textbook will say MA UA, that will give you, they can call this small m and call the total of this plus this as capital M times what? V. It doesn't matter. And they can just call this U. So it doesn't matter. Still the same thing, because you only have one mass here, which is the mass of the bullet. Mass of the wood is none of our business, because the wood is stationary. So we're just using the mass of the bullet. So this principle also occurs in bullet and wood question. Bullet and wood question. We are going to come across that. So instead of us going through this long procedure, now we are going to make use of this, as easy as that, where M here stands for what? The mass. The mass of the bullet. This is the speed or the velocity of the bullet. This is the combined masses of both what? The bullet and the wood. Of course, they will move with a common velocity, V. So with this case, this is also applicable if they want to select bullet and rifle. It's still the same concept, bullet and rifle. So in that case now, this is the mass of the rifle, while this is the speed of the rifle. So it depends on the question, they all follow the same concept. Okay, now with this now, we can simply or quickly do some exercise and see. Let's use an example. Our example may not treat all of them. You can just pick one of the cases and do the example. But for more questions, go to the exercise section and pass question. You will see that it touches virtually all the cases. Let me quickly talk about the energy loss, because remember, energy loss can only occur in an inelastic collision. Energy loss only in an inelastic collision. So they can ask you to calculate the energy loss. This can only occur in an inelastic collision because energy is not conserved in inelastic. So remember, kinetic energy before collision is always greater than kinetic energy after collision, provided that collision is inelastic. So if you're asked to calculate the energy lost, it's very simple. It is just kinetic energy before collision minus kinetic energy after collision. This is simply the formula. So it now depends on the case you are dealing with. So if you watch your case, you can simply, I've already shown you how to do the kinetic energy before collision and how to get your kinetic energy after collision. So once you get them, subtract them away. That is what you call energy lost. Remember, energy loss can never be asked in elastic collision. Only in what? Inelastic collision. So let's quickly solve an example now. Now we have a question here on the board. Now let's see which of the cases this question addresses. Now what we have here, the question says, lead bullet of mass 50 grams is fired with a velocity of 200 meters per second into a lead block of mass 950 grams, given that the lead block can move freely. So first of all, before we start solving this, I think this is referring to the last case, which is sixth case there. Now we are talking about a bullet and a block. So the block is stationary, it's not moving. At initial, that is before the collision, it wasn't moving, but we are now told here that after the collision it moved, given that the lead block can move freely. So after collision, this bullet had an impact, so it moved. So the question now says, the common velocity after impact, which means there was a movement. The common velocity after impact, I says the kinetic energy after impact. After impact. Now we have I, the loss of energy. The loss of energy. So we are going to solve them one by one. So the first question is the common velocity after impact. If we put down our solution, so we have I question, the common velocity. Now we know our formula is simply mass times what? The mass of the bullet times the velocity of the bullet is equal to the total mass. The total mass, like I say, the total mass of both the bullet and the block times the common velocity of movement. So in this case, what we are looking for here is V. That is what we are looking for, V. Now this, we can expand this. This is mass of the bullet times the velocity of the bullet is equal to mass of the bullet plus mass of the block. So both of them are BB, but it doesn't matter. Okay, now what we have here is V, if you make V the subject, is equal to mu divided by capital M. Mu, small mu, divided by capital M. Now what will this give us? That V, which is the common velocity, is equal to mass of the bullet is 50 grams. So before we solve this, momentum deals with kilograms, not grams. So we have to convert this by dividing by 1000. So what we have here is 50 over 1000. We have converted to grams times the velocity of the bullet, which is 200 meters, divided by, now we have to also convert this. Now this is the sum of both the mass of the bullet and the mass of the block. So what we have here is 50 divided by 1000 plus 950 divided by 1000. This is what we have. So we are going to use our calculator to machine everything out. 50 divided by 1000 should be giving us 0.05 times 200, everything divided by 0.05 plus 950 divided by 1000. This is giving us 0.95. And if I clean this side, what I have is 0.05 times 200, then V is equal to 10 divided by 0.05 plus 0.95 is 1. So our velocity, common velocity, is 10 meters per second. Always remember, always remember to convert from grams to kilograms. Very, very important. Always remember to convert from grams to what? Kilograms. Now let's quickly solve the kinetic energy after impact. The kinetic energy after the impact. That is I question. So let's clean this. Remember, kinetic energy is half mv squared. But in this case, we are talking about after the impact. So the mass we are making use of is the mass after the impact. The velocity we are making use of is the velocity after the impact. Therefore, the kinetic energy after impact is half capital M times the common velocity. So what we have now is half into 0.05 plus 0.95 times 10 squared. Times 10 squared. So when we do that, we have 10 squared is 100 divided by 2. So what we have is 50 joules. 50 joules. This is 1. 10 squared is 100 divided by 2 is 50 joules. So be very careful. Always read your question very well. They said after the impact, that is after the collision. They did not say we should calculate the kinetic energy before collision. No. They said after. So we are making use of the total mass when they have collided times the common velocity after the impact. Now the next question here says the loss of energy. The loss of energy. I've told you, energy loss can only occur in what? Inelastic collision, when they join together. So how do you do that? And loss in energy is simply kinetic energy before impact or before collision minus kinetic energy after the impact. It's as easy as that. Now, we have calculated the kinetic energy after the impact in the previous question and we got 50 joules. So we can just put that down. The kinetic energy after the impact is 50 joules. So we don't need to repeat it again. Now let's calculate the kinetic energy before the impact. Remember, before the impact, kinetic energy before the impact. And that is half mass of the bullet only, that is small m, times u squared. Be very, very careful. Always understand your question. So what we have here now is half. The mass of the bullet in in kilogram is 0.05 times this is 200 all squared. 200 all squared. So let's multiply this with our calculator and see what we have. So when you multiply this with your calculator and divide by 2, so I believe what you have is 1000 joules. 1000 joules. So this is the kinetic energy before the impact. Why we have this as 50. So if we put it here, the loss in energy or the energy lost is simply kinetic energy before this is 1000 minus this, which is 50. So that will give us 950 joules. So it's as easy as that. It's just your ability to understand what the question is talking about. So if you have any question concerning what is on the board, drop your questions in the comment section. I will attend to that. But if it is clear, you are welcome. Please always share. For more of these particular questions, go to the past question sections and the exercises. You will see more of these questions.